Hello. Hello, Mr. Ari, are you alright?
Yeah.
Okay. So yeah, we have been talking about this human gene problem. Yeah, we have this A. So this DNA thing. A pair with T, C pair with G. Right? A pair with T, C pair with G, and then it could be many. Right? So we want to find out the gene mutation group. Right? Gene mutation group. What gene mutation group? It differs only by one gene, right? For example, ACCT and CCCT, it belongs to the same mutation group because they're only one difference. And AGCTT, AGTTT belongs to the same group, right? But AGTCT is not, right? Because it differs. Or this one and this one is, right? Differ. But this one and then this one, is it? Look.
No. But the second one and third one are.
Yes, but okay, that's the thing. Look, because this one connects to the second one, right? So this one, yeah. AGCTT. AGTTT. And the second connects to the third, yeah? AGTCT, right? Yeah? Yeah? So these two belongs to the same mutation group, okay? Do you understand? Because there's a connection, right? So the first day, the day before yesterday, we talked about depth search. Yesterday we talked about breadth search, right? So this is a graph problem. Graph. How do you spell graph? GRAPH. Is a graph is a collection of vertex and then edges. Right? And then now we have a vertex. This vertex is the genes, right? The gene group, the gene. And where are the edges? Where are the edges?
The edges are there.
Yeah, but the problem, you see, this problem statement does not give you the edges directly, right? It does not tell you, okay, these two gene belongs to, there's an edge, there's no. But how do we find it out? There's a rule, right? We check if these two belongs to some mutation group, but only one, right? So if there's one letter difference, then there's an edge, right?
Yeah.
And our task is that, look, we have a several vertex, several genes connected by edges, and we want to find out how many number of the connected groups. In this case, there's two, right? Do you still remember the depth search?
Depth search is traveling by, you're like traveling from node to node by traveling along the edges.
Yeah, exactly.
And
so
then,
yeah.
And then you go no more.
That's right. And yeah, quite right. Yeah, you're quite right.
Yay.
So I'm just writing that thing here again, okay? Define, okay, let's say find number of mutation group. And we're given the gene. Look at these genes are the vertex, right? Okay? So look, we have a depth search or breadth search, yeah? Could be depth search, breadth search. And then we just don't implement here right now. So look, we have answer. This is the number of group. Then we can say for I in gene, right? We go through each gene group, right? And if I still in left, remember the first one, the left equals same gene. If still in the left, and then we do what? Depth search I, right? Yeah, depth search I, and then answer plus equal 1. Right? Look. Yeah? So what is this depth search? You will remove all the vertex that connected to I. Okay? Alright. Return answer. Yeah, we talked about that the day before yesterday. Look, this is I, yeah? We go through this I. Look, this is the gene. Yeah, there might be some group, right? Some group like that, right? Right, here, go through the I. And then once I do this depth search I, then the first thing I need to do is A don't remove A. Left don't remove A. So what does it do? Then you will remove it from the genes, right? Remove it from the genes. So you remove all these things. So next time you go here, look, I found another group, right? I found another group. So answer equal plus equal 1. And look, this depth search. The order of marking the nodes doesn't matter here, right? That's why we can use the breadth search. Make sense? Because all my target is to what? All my target is to what? To remove all these as a whole. I don't care in what order I remove them, right? Make sense? So I can do breadth search, I can do depth search. Depth search, recursion, stack. Breadth search using the queue, level by level, right? Look, this is 1, this is 2, this is 3, 4. Depth search, alright? Depth search, 1, 2, 4, 3. Breadth search, 1, 2, 3, 4. Make sense? Okay. So, do you still remember a data structure which is perfect for this kind of purpose, right? So we want to find out the number of the groups, and at the beginning we have n groups, and then we can, if there's an edge, we mark it as a group. If there's an edge, we mark it as a group, and then we can find out the number of groups. What do you call it? Remember? Do you still remember?
No.
A data structure.
Disjoint set.
Yes, exactly. Disjoint set. Disjoint set. UnionFind. Disjoint set. Disjoint set. Okay, and usually we can do this UnionFind. So what is UnionFind? So this disjoint set is a data structure which supports at least these two kind of operation, which is union, where another one is find. So union, you have two groups, you union them together, union, yeah, united, union. Find, you can tell if a vertex, if an element belongs to which group, right? Okay, so I'm just quickly writing this disjoint set thing here, okay? I think we talked about that a long time ago and you may forget a little bit, but that's alright, so we can revisit it now. Define UnionFind. Okay, that's UnionFind. That's a class. Oh, actually that's a class. Class, and then we have a init, which is the constructor. And then we have what? Sizes. We want to put a size, which is a dictionary. And we can have you can implement this as a fixed size. You can pass a parameter which is n and a number of groups. Right? If you know the number of groups, then you can pass the n and then create a static array with n size, with n element. But we now use the dictionary, which is the more flexible. Okay, self.parent. Parent, as we call it part, okay? Okay, and then two things. One is the find union. Find, let's say if we want to find A. Yeah, if it's not in there, then we return what? If we want to find it. So if it's not in there, what should we do? What should we do? We first of all, if A is not in self.parent, right? If it's not there, what should we do?
We throw.
What should we do? So look, if an element is not in a parent, then we want to set it, right? We want to set it, right? Yeah. So we can say self.parent. Sorry.
Set it.
Yeah. Pay A equals what? A. Okay. It belongs to itself. Right? If it's not A, if it belongs to the self, then like sizes at the beginning, size A will be equals 1, and then we can just return what? Return. We want to return the number of the group which is this right? A. Okay. So because look at this, actually this is okay. So this is the class. So we need to we need to put the first parameter as self to say it's a class method. Okay, self A. Right? Otherwise, look, if not, okay, if self dot parent A not equal A, right? If this is not group, then we can say what? Self dot parent A equals self-defined, and then we pass this in, okay, self.parent A, okay, and then we do this return self.parent A. Okay? I explained it a bit. So this thing, okay, we want to find the parent. We want to find its parent, and look, if its parent is not there, then we set it to a parent, and then we return, also set the size, and we return A. If this, look, what does this mean? Look, if this is A, okay, then if this edge is, look, Eric, I want to find this. Yeah, I want to find this, A. But now it points to B, and it points to C. So because A's parent is not A, and then I need to do what? So self-parent A equals, I find this one, and which is again points to this. So eventually I want to compress the path, because look, eventually if the path is too long, then this operation self-find will be take linear time, right? So if I do this, the next time I know I want to point it to what? I want to point here to here. I want to point this thing to here. Okay, I want to shorten the path to look it up. Right? So ideally I want this kind of structure. This is parent, this is group A, and then I have these two that belongs to the same group, okay? Yeah? You see? These, look, 2, 3, 4, 5, and 1 belongs to the same group. 1 points to itself, which is points to parent A. 2, parent points to parent A, right? To parent 1. 1 points to parent 1, right? So that's why it is return self A. This is better than this. This is better than that. Yeah? Yeah, if you keep a UnionFind data structure like that, what kind of problem would be like? It will increase the lookup time, right? Because look, I want to check out the group. What's the group for the parent? What's the group for 5? He said, okay, it's the same group as 4. Okay, what's 4? Same group 3, 2, 1. It needs to look it up here. So it takes time, right, to go this way up, right? But now, look, I get this parent, and then I reset it. So look, 5, eventually it will tell me it's 1, right? Yeah? So instead of pointing to 4, I then point to 1. 4, it will tell me it's 1, right? Right? But now it points to 3. So to the next time, I don't want to go through this again, so I point to 1. 3 points to 1, right? It's the same group as 1. But now it tells me it's the same group as 2. So now what do? I point to 2. Right? So in this case,
it looks like a strawberry.
A star, right? So next time, look, 2, what's the parent of 2? It's the same as 1. Okay, 1 is 1, and then just one lookup.
Why does the note 5 have 2 arrows?
Okay, I haven't. Yeah, it's the same. Yeah, you see? Do you see this getting it? Yeah. So this is called the compress the path when lookup. Compress path when lookup. Okay. So self-defined. Okay, this is self-defined, and then with the self-defined, we have also another thing, which is called union, right? Union. Wait, just needs to get a thing. Union. What does union do? Union you will tell, okay, 2 nodes belongs to the same, right? Define union. Self A, B, okay. So then what should I do with that? First of all, we need to check if 2 equals the same, right? So now look, we can say, okay, let's say x equals self-defined. We know that self-defined A, right? And then y equals self-defined B. If they belongs to the same group, what should we do? If already that belongs to the same group, what should we do?
We should just relax.
That's a very good answer. Relax, yeah, return. We can just return, yeah, because it's already in the same group, right? Yeah, in the same group. Just return. Okay, now look again. Let's visit it. Look, so I have these. These. Only 1, 2, 3, 4. 4 nodes, and then I have like 100 here. I have.
then
So do you think? Okay, Eric.
that's a lot.
So now I'm telling you like okay, I want to this.
Spider-Man.
Yeah. This is A. This is B. Now I tell you I want to union A and B. So do you think which one is better? Putting A to B or putting B to A?
A to B.
Why is that?
Because A has
Less nodes, right?
less nodes.
If we putting B to A, what happened?
Take.
What happened? I mean, what happened? What do you think? Because eventually, look, if you put the B to A, then the next one, the lookup, you will have more nodes to compress, right? You have more nodes to handle because these eventually will be relocated, the path, right? So it will be more work to relocate all these nodes to reassign to A, right? But now if you look, if there's just one or two nodes, you can just do it one or two nodes. That will be easier, right? Yeah. So then we need to tell the sizes. If self dot sizes x, right? It's x, right? Smaller or if it's smaller than self dot sizes b. Y, and then we just swap it. How do we swap it? X, Y, how do we swap it? How do we swap it? How do we swap it? If we want to swap...
Like something equals something.
Okay, so XY equals YX. And now I want to... Now X is bigger. So I want to merge Y to X, right? So I have to say self.parent. I want to put a Y to X. X is bigger. X is bigger. So I want to assign B, the parent of B, Y equals to X. Y equals X. Right? And then now I want to update the sizes. So self dot sizes X, right? Because I put a Y to X. So the X sizes will be having addition original self dot sizes Y, right? Yeah? Right? Make sense? We can return false here, and then we can return true here, right? To indicate whether we succeed the union, right? Make sense? Yeah. If self the size is a x smaller than y, yes. Okay. A is bigger than A is bigger. Yes. All right. Yeah. Okay, and then another operation is to get a count, right? To get a count, define the count. Count self. This returns the number of connected groups. Anyway, so it's a property value. You can say property value. Yeah, property value. So with this one, we can just return the number of count. Return if the parent is a dictionary. Yeah, x. If it's a group, right? If it's a group, then x will be the same value with x, right? So I can just return what? I need to sum. Okay, sum what? X equals or y for x, y in self dot parent dot item. Right? Am I right? Right? Okay, so this is the UnionFind. Okay, this is the UnionFind. So how can we use it as the how can we use it in solving this kind of problem here? How can we use this in solving time? So we can look, Eric, look. Let's look at this. Okay, look. We have a node, right? Yeah. We have that's a few nodes, right? So look, if we know these neighbors, we can just union them. Yeah, union. Yeah, union this, and then we can union this, and then later we just find out how many connected groups. Right? Make sense?
Oh yeah.
So it'll be easier. It'll be very straightforward, intuitive, right?
Yeah.
Intuitive. Let's say define. Let's say find groups. Mutation.
Oh, yeah.
Genes. Okay, so now again we want to find out what? We want to find out the g equals g set.gene. What's the advantage if we convert the list to the
It will be more
what?
faster for the lookup.
Fast O1 lookup, yeah, well done. Okay, now UnionFind equals UnionFind. That we just define this structure, and then we go through the list. Therefore, I in G. Yeah, for I in G. Now we want to find out for, okay, let's say for J in range, length I, right? We want to find out the neighbors. Alright. Why you draw on my desk?
It looks good.
ACCT. We want to find out the neighbor. How do we find out the neighbor?
A is paired up with T.
Yeah, but no. I mean the how many?
A has other choices of C, T, and G.
Yeah. So for each letter, I want to try the neighbors, right? And I want to find out if it's in there, right? So look, the neighbor will be what? G up to I. I want to pick the up to I choice and replace with. Okay, I need to go through that thing again. For X in A, C, T, G, right? This is the four choices, and then this current one is what? I up to J plus X plus I J plus 1 to the n, right? Yeah? Okay, so look currently, Eric, look, currently this is J here, right? So what's its neighbor? I can pick the letter up to it, which is A, and plus their four choice, yeah? A, C, T, G, and then plus what? Plus the next letter after it will be C, T, right? Do you get it?
Plus.
This is what it means here. So when I am at index J, I have four choice, and then I can pick the letters before it and the letter after it, concatenate it, right? And then what's next? Then I can say if n is in G, right? This is O1 lookup, right? And then what do we do? UF dot union, union I with n, and then what do we do? Return UF dot count. Okay, this is a property, so we don't use the bracket to call it, right? Yeah. Alright, make sense?
Mugs.
Yeah, make sense?
Makes sense.
Do you understand this one? Do you understand? Look, let me repeat again. Let me repeat. UnionFind. We define this UnionFind data structure. Set. We convert a list of vertex genes to G, so we can use the O1 constant lookup. Okay. Yeah, O1. No, there is no dot. Okay. Look, when we go through each vertex, for each vertex, I generate its neighbor, which is its mutation, right? This is generate the mutation. Okay, what's this? Anyway, I'm testing. What's this?
That's if
the mutation
the mutation is in the G's.
if we have the vertex, right?
Yeah.
If we have the vertex in the group, then what should we do now?
We shall look for A, C.
What should we do with the union?
Union.
Current vertex is I, right?
Yeah. And N.
Current vertex is I. And what's N?
N is A.
The what? What's this? The neighbor.
Neighbors.
So there will be four neighbors. So look, I'm visiting vertex I, right? I'm visiting and I connect all its neighbors. Okay, so here there's a mistake here. I need to remove it. Yeah, G don't remove. Yeah, do I need to remove it?
Yes.
Because I already visited, I need to remove it. Yeah, am I right? Yeah. Do I need to remove it? Probably not, right? Do I need to? Probably no. Probably we don't need to remove it. Do we need to remove it? We can union it. We probably don't need to remove it. We probably don't need to remove it in this case. So if it's already in a G, if we have this vertex in the graph, then we union I, because I and N are neighbors. They belong to the same group, right? So yeah.
Yeah.
Okay, so let's
They
try.
belong in the same group.
Okay, so let's try. Okay.
I'll write it down. They belong.
Yeah. Then let me write it, and then can you simulate this process? Okay. Can you simulate this process? Okay. I have this ACT. Let's just try easy. Okay. CCT.
Join.
TT. And then wait. CCA. Okay. And then TTA. Okay, so there are 1, 2, 3, 4, 5. 5 nodes. UnionFind. Okay, you can say okay 1, 2, 3, 4, 5 the list. Okay,
I
so
convert it into the.
yeah, that's fine. So I'm here ACG. Okay, I'm ACT. So now what should I do? Where is the neighbor? Which one is neighbor?
N.
Yeah, neighbor. So which node is its neighbor? This one. Okay, so I connected. Yeah, Union. Okay, does it have other neighbor with this one? No, right? Not directly, right? Okay.
Yeah.
Okay, so now I try with this one. Probably, yeah, we don't need to remove it. If we remove it, that would be a mistake. Okay? We don't remove it. Oh, here's CCT. Where is the, yeah. You see? Okay. And then, does it have any other?
No.
Okay. TTT. What's its neighbor? General is neighbor. Which one is its neighbor?
TTA.
Yeah. Okay. And then CCA, which is neighbor, this one, but we already merged it. That's fine. We can do it again. Yeah. And TTA. Okay. So that's why we don't remove it. Okay. Yeah. If we remove it, what happens? If we remove it, then for example here, I join this one and then remove it, and I can't find this one. Do you get it? If we remove it, and who connects to this? Nothing. Right? But we eventually need this to connect this. So after this, uf.count, what's the answer?
2.
We're done. That's it. Got it? Make sense? Yeah? So which one do you think the better? I mean, you understand the most, or you can implement it. How many ways of solving this problem?
About a lot.
How many days we talk about this?
A few.
What is a few? I mean, how many days we solve something? Yesterday we talked about what?
We talked about the gene being listed.
Yeah, I know, it's the same thing. So what kind of algorithm? I just talked at the beginning.
Gene.
What kind of algorithm? To solve the problem, how do we search it?
We search it in breadth search, depth search.
Yeah, okay. Breadth search, depth search, and this UnionFind. So how many ways of doing it?
3.
Okay, which one you think you can understand the best?
I'm not sure.
Which one you think you like the most?
I'm not sure.
You're not sure? Come on, pick one. Which one you like the best? Which one you think is the most easy way to understand? I mean, or which one you think is the most intuitive way of solving this problem? I mean, there's no right or wrong answer. I mean, just a quick survey.
I'm not sure.
You're not sure?
Yeah.
What do you mean you're not sure?
I'll just choose this one.
Choose this one. You think it's the best, yeah?
Mm.
Okay, that's it for today. Bye-bye. Bye-bye. Come on.
Bye-bye.
Say bye-bye.
Bye-bye.
Bye-bye.